We had seen that an electron moving in its orbit could be considered as a current-carrying coil. Therefore, it would have a magnetic moment. In this case, if we look from the top, then the movement of the electron is in the clockwise direction, which is equivalent to a positive charge moving in the anticlockwise direction. Then, from the right-hand rule, we have the magnetic moment pointing upwards. Whenever we think of a current-carrying coil, it would be equivalent to a magnet with the same magnetic moment. So in this case, the magnetic moment is upwards, since the electron rotates clockwise when viewed from the top. So you can think of this electron as a tiny magnet with its north pole upwards and the south pole downwards. Let's take a piece of metal, and for the sake of simplicity, let's say we have just two atoms, each with one electron rotating. This is just a hypothetical example. You can see that they do not rotate in the same plane. The net magnetization of the material depends on the orientation of these two magnetic moments. In this case, since they are not aligned, we can say that the magnetization is partial. Let's look at some other extreme cases. In this case, the magnetic moments of both the electrons are parallel and they point in the same direction, that is upward. In such a case, the magnetization is maximum. You can think of this model in terms of small magnets where all the individual tiny magnets are aligned. So their magnetic moments are aligned, thereby providing the maximum magnetization. Here, the magnetic moments of both the electrons are antiparallel. The electrons actually rotate in opposite directions. The magnetic moments point in opposite directions, that is, one downwards and the other upwards. In such a case, the net magnetization is zero. So if you think of this model in terms of small magnets, they are cancelling each other's magnetic moments, thus yielding zero magnetization. Take the case of these two metals. In metal A, the magnetic moments are all aligned, whereas they are not all aligned in metal B. So the net magnetic moment of A is greater than the net magnetic moment of B. A and B have equal volumes. Magnetization is defined as the net magnetic moment divided by the volume. So the magnetization of A is greater than the magnetization of B. For metals with a higher magnetization, the magnetic field is stronger. Since the magnetization of A is greater than the magnetization of B, the magnetic field of A would be greater than the magnetic field of B. So the magnetic field is proportional to the magnetization. The higher the magnetization, the greater the magnetic field. The magnetic field can be expressed as μ0 times the magnetization m. We have seen this earlier, that a solenoid creates a magnetic field. Let's say that this magnetic field is B0, and B0 is μ0 times n times I, where n is the number of turns per unit length. Now we have just seen that μ0 times the magnetization is equal to the magnetic field. So we can write B0, the magnetic field, as mu0 times h, where h is the magnetization, which in the case of the solenoid we can call as the magnetic intensity. The greater the current, the greater the h, or magnetization, or magnetic intensity. Now what would happen if we put a piece of soft iron in the cavity of the solenoid? The soft iron has a certain degree of magnetization, which is weak, since you can see that all the magnetic moments are not aligned, but now they are placed under the influence of B0, the field created by the solenoid. Under the influence of B0, the magnetic moments begin to align with B0. So, in a way, this is induced magnetization. Not all of them may align, but a majority of them do align. Some of them tend to align, but not completely align. The greater the magnetic field of the solenoid B0, the greater the amount of alignment. So if the magnetic moment of the soft iron aligns, what would be the consequences? When this alignment of the magnetic moment takes place, another additional magnetic field, Bm, is created due to the aligned magnetic moments of the soft iron core. This field, Bm, is in addition to the field created by the solenoid, B0. So now the total magnetic field has increased to B0 plus Bm, where B0 is the contribution by the solenoid and Bm is the contribution by the soft iron, by virtue of being in the magnetic field B0. If the magnetization of the soft iron piece is M, then the magnetic field due to the soft iron material is mu0 times M. So by introducing a piece of soft iron, the magnetic field can be made stronger.